So lastly, we're going to talk about the row space. And this is the span of a set of vectors a1 to am. And we're using lowercase a's here to indicate that this is different from the column vectors that we would have had in our column space. And these are going to be the row vectors of a matrix A. And this is what we're going to refer to as the row space of a matrix A. And just a quick example here will give us what we want out of this. So we'll take A to be equal to just a simple matrix 1, 2, 3, 1, 0, 1. And again, we're looking at this from the row standpoint now. So this top row and this bottom row are what we're looking at as the vectors horizontally instead of vertically like we have been. So we have that using the notation above, A1 would be the first row associated with a vector, which would be 1, 2, 3. And of course, then A2 would be equal to the vector in the second row, which would be 1, 0, 1. So pretty simple in terms of what we want the row space to be. And we can talk about, again, the span of those rows, much like we did the span of the column space being the range. Here, the span of this is a different subspace, but it is a subspace. And there's a theorem also that we get here that's going to be useful for us. Our particular concern with working with the row space is not necessarily to do a lot with it, but we can actually utilize this theorem to help us with something that we're going to be working on in a little bit. So let's let A be an M by N matrix. And let's suppose that A is row equivalent to another matrix B. In other words, we've done a row reffing process on it, so they're row equivalent. Then A and B, both of these matrices, have the same row space. This is what our theorem tells us. And again, I'll give us an example here to take a look at. So we'll take A to be equal to the following matrix: 1, 2, 1, minus 1, minus 1, 1, 1, 4, 5. And if we were to plug that into Octave and row ref it, we would get 1, 0, 0, 0, 1, 0, 3, 2, 0. So there's our row ref version of that matrix A. So these are considered to be row equivalent. And what this theorem says again is that these two matrices, although they look very different, will produce the same row space. It's just that the second one, you'll notice we get a row of all zeros. So we can get the same row space with just two vectors that we would have had from the original matrix here using three vectors. So it's a little bit more efficient in how it generates that same subspace. So suppose we want to do this with a span or a range of a set of vectors. In other words, if we wanted to try and use a column space and somehow reduce the number of vectors we needed to generate the same range, how could we do that? And it turns out that this process only works for the row space. But there is a little bit of a trick that I'm going to show you. And I think an example will illustrate this the best. Here's our example. We've got four vectors that are going to be in R3, and they're defined as you see below. And what we want to do is, again, try this little trick to allow us to see if some of these vectors might be removable. In other words, maybe I can generate the same column space or the same span for these column vectors as we would have using all four with less of these. So the way that we do this is first throw them all into a matrix. So I'll make a matrix A that will consist of all these column vectors. So there's our matrix. And so this process of kind of creating these row equivalent matrices only works on a row space. What we'll go ahead and do is transpose the matrix. So we'll take a transpose. And you'll remember that just means rows become columns. And we rewrite it as 1, 2, 1, 2, 3, 5, 1, 4, negative 5, and 2, 5, negative 1. So there's A transpose. So now the vectors that were columns become rows. Well, now we can apply this row reffing process. Again, when we use Gauss-Jordan elimination or RREF, it only works on a row equivalent basis. There is no system that allows you to reduce these column by column. So we can transpose the matrix though, and then from there we can row ref the transpose matrix. So we get a new matrix B that is row equivalent to A, transpose, and that's going to look like this. So RREF A transpose, and that's going to be 1, 0, 0, 0 to 1, 0, 0, 7, minus 3, 0, 0. So we got 2 rows of zeros at the bottom here. So this matrix B that we're talking about that's row equivalent to A transpose has our vectors in it. It's just that, again, these vectors are in the rows. So we can transpose one more time to make it look similar to what we had when we started. So now we take B transpose, and that's going to give us 1, 2, 7, 0, 1, negative 3, and then a couple columns with just zeros in it. So now what we've done is played a little trick on our matrix A to create a sort of, if you will, column equivalent version of that matrix. And you can see we can actually wipe out a couple of columns here and generate the same range for A using only 2 vectors. So in this case, we get 2 vectors that generate the same range as all 4 of our original vectors that we had in our set. So what we would generally do then to compute this is to do something like RREF of A transpose and then just transpose it back one last time. So we now have a new set of vectors that produces the same column space, but does it with fewer vectors. In other words, 2 of the 4 vectors are not needed to produce the space. In this case, it turns out that that's a plane. We also see that if a set of vectors is linearly dependent, it means that we have extra vectors that we don't need to generate the same space. The downside here is that the new set of vectors is different from the starting set of vectors. In many cases, this is fine, and we don't really care, but if we need to use the original vectors, we need to find a way to somehow choose which vectors to drop, and that's something that we'll explore in another lesson. For now, I've got a set of vectors below, and you can see if you can apply the same process using Octave to generate a smaller set of vectors to get you the same column space or range.